by the kind of troubles we have, you can kind of see what's the difficulty of building a interferometric detector. So if you thought it's tough, it's not so tough, because I have about the same amount of problem with interferometry as with this presentation. Let's see. So I'll repeat some of the things Peter said, but with some more details. It's a kind of problem with the language in talking about these things, because the detectors are kind of coming and going away, and when we talk about, sometimes when we talk about the present, we really mean the future. And that's our, in an optimistic field, that's just how the language is. When I started in this field, it was in the 20th century, so it's a long time ago now. And at the time, there were no operating large interferometric detectors. Everything was a prototype, and the bar detectors were on. And our challenge was to somehow overcome the bar detectors' sensitivity. We thought that would lead us directly to detection. And so at the time, and then over the next few years, they came up. And the ones which came up in my first generation are these ones on the left. So there was, besides what Peter mentioned, there was also a 300-meter detector in Japan, which was really the first large-scale one. And at the time, there were also several bar detectors. I think Sujan's question was pretty good. It's even, the Earth-Moon baseline is pretty tiny, and people have bigger aims. So there is a LISA project, but really the full size of the galaxy is used for the baseline and the pulsar timing network. And yeah, these are detectors which I think are sort of real and are happening. And these other ones, well, BBO anyways, and things of that sort are sort of super follow-on detectors, which are envisioned for 50 years or more in the future. So we describe them as concepts, but you shouldn't confuse things which are like this with, these are gray in my slide just because they're kind of in the past. These are colorful because they're real, and these are looking like this because they're just imagination.
If you add pulsar timing, then maybe you should add CFD polarization. That's a gravity detector, even bigger.
I'm being recorded here, so I can only, there's only some kinds of comments I can make. Yeah, so this is just some more detail on the Weber detector. This is a picture of, here's Joe Weber, and here's the bar. You can, I think you can see him. I think you can see him okay. He looks a little bit of like a crazy mad scientist. And I like to think that it took somebody with that kind of, if it had been me in that year in the early 60s and I had known anything about what the real numbers were, I would have not begun this field. I would not have thought, yeah, let's do something that will take 50 or 60 years to come up. But he was the kind who could see this kind of thing. So this is the piezoelectric transducers that Peter mentioned, and this is one of the later bars. The first, I saw several of the early bars sitting around in one of the old labs, and they were of this sort, and he had done some machining in the middle to do what you were mentioning, to make the first acoustic mode lower. But one of the, I think as it turns out, one of the key reasons that they were this big is that if you think about the resonant response of a harmonic oscillator to this external force, then exactly on resonance, some of the frequency terms vanish, and you get a prefactor which is like the mechanical Q factor divided by the frequency squared. So the frequency does come into it, but it's not so strong as it is. Off resonance, you don't get this Q factor. So if you can make a large system which has a Q of more than 1 million or so, then the resonant response is stronger than you would get for just a free mass, because the Q overcomes this. So it's worthwhile to do. This is a comparison of the best strain sensitivities of all of the detectors, sort of at the end of the 20th century, where they were at their peak. So they could get peak strain levels that were almost 10 to the minus 18 in strain, and the strain noise, just to compare with the kind of spectral density we have. This is a difficult exercise to do. So I had to get a lot of help from the bar people to learn how to turn these units into the interferometric units, but it's something like this. The other thing that it's easy to forget, I guess, is that in addition to the work they did on cryogenics, uh, the work that it took to do the real quantum limited readout, or almost quantum limited readout for the bar detectors, completely translates into both the gravity wave interferometry field, and we use all of that language, but the whole field of quantum optomechanics is leveraged on this technology and this early work into quantum limits that the bar people did. Just some more pictures. This is the last several bars. There were most of them in Europe here, Auriga, Nautilus, Explorer. There was one here in Louisiana, which it's no coincidence that the LIGO interferometer is now in the same place, because it's probably this guy here found this area. And then there was one in the southern hemisphere, this niobe detector made of niobium, made by David Blair's group in the University of Western Australia. And this one was the only one which was sort of at this lower frequency. It was really a huge bar, so 700 hertz instead of 900. And they also did a lot of work on cryogenics, as Peter mentioned, but now that we're in the phase where we're also thinking about using cryogenic technology for interferometers, we take it under advisement that the effort to get gravity wave bars to work at millikelvin temperatures was extremely tough. And so it's not only do we learn by their successes, but we also learn from the troubles that went into this. We think so because we never detected anything. Do you mean for these? Yeah, this is, I mean, it's a very active area of research, and we're not really getting signals where the signal-to-noise ratio is less than 1, but we're trying to get the best signal detection statistics when the signal-to-noise ratio is maybe 3 or 4. And it's just done by a lot of filtering and rejection of background events, making the statistics of the noise to be very Gaussian and so on. But I suppose maybe another answer is, if it's true that this next generation of detectors will make weekly or monthly detections, that the signal-to-noise ratio in the current generation of detectors must have been around 1 or 2. So we don't really know what the true signal-to-noise ratio is because we don't have any confirmed detections, but we have some estimated bounds based on what we expect the population to be. Anyway, so that's all about bars. And at the Friday, we'll talk a little bit about space detectors and future detectors. But for today and the rest of the week, today and the rest of this talk, I'll just survey some recent past interferometric detectors, and then also the current generation of detector. And then the rest of this week, we'll describe the details of the technology which go behind it. So I'll kind of skim through it quickly here, and feel free to ask questions, but the real details will come later in the week. There are a lot of technical problems to doing the detection, but the two main challenges really are the quantum mechanical limits in doing interferometry, and then the thermodynamic limits of these test mass mirrors that we use to do the detection. So there's some thermodynamic vibration of the mirror surface, which limits how well you can use it for displacement measurement, and then just this act of using a laser field in order to interrogate these masses has some quantum back action limits. So tomorrow in the morning session, I'll go through all kinds of details about this quantum back action limit, and then I think in the next day, it's maybe on Wednesday, it's thermal noise, perhaps. I don't know if can you read this text from in the back? No? Good. I'll read it for you. I love to read this. This is a particularly good kind of whiskey. It's from the island off the west coast of Scotland, Islay. And they had an advertisement concerning Michelson's interferometer around the time that the Michelson interferometer was a new scientific discovery. And they say, well, I can't even read it. It says, the Michelson interferometer is as confusing as it sounds. and even more complicated than it looks. Designed to detect minute variations of light velocity through ether in space, it ended up proving that the ether was not there in the first place. Little wonder that the distillers of Bunnahabhain, 12-year-old single malt whiskey, have no time for such scientific contraptions. So this is the Michelson Interferometer, right? It's like touched off the whole field of relativistic measurements and precision measurements. It's a wonder of today. Any of us would be proud to have invented this thing. And this was the public reaction to it. And anyway, so I thought it was cool, so I called them up, and Lillian over there sent me this photo of they have an original copy of the advertisement. So whenever we think that we're doing some sort of thankless task and getting not enough reward for our research, I think even Michelson had this kind of trouble. So anyway, this is a picture of his original one. And now we think about it with the laser beam, but truly the Michelson interferometer never really had coherent light source. It was just whatever, I don't even know, maybe a lamp of some kind or sodium, some sort of light. What? Yeah. Yes, that's right. That's a good point. Yeah. I don't know if this was as good in Michelson's time, actually. This is really good now. So it's difficult. I mean, we have very good technology. Michelson had a heavy table, some optics, which were not so good. But even then, he was able to get better than, I think he was approaching 1/100th of the wavelength in terms of how good his interferometry was. It was somewhere between 1/10 and 1/100th at long time scales. So pretty tough. This is a somewhat more detailed, I say cheat sheet, because if you Google for something like Emacs cheat sheet or VI cheat sheet, you get something which is like this for those programs. And this is it for the Michelson. How does the Michelson interferometer work? Well, the laser field comes in, it bounces around here, and if you set the length appropriately, you can set it up so that it's mostly destructively interfering here and constructively interfering going back. And then if you plot the laser power at this port from this photodetector as a function of the displacement, you see this up and down thing where you have constructive and destructive interference. For gravitational waves, what happens? Well, if you have a wave come through, you get this strain in space, as Peter was showing. And that looks like a phase shift on the light. And the phase shift that you get, this phi, is proportional to the strain times the length. So more length you get, the more phase shift you get. That's good. And this is the phase shift depends on this apparent length change like so. So you would also win by having a smaller wavelength. That's true. The signal that you get, the slope change in power versus change in phase, is also proportional to the power which is incident on the beam splitter. So having high laser power is good. That's all of these things are good. Good length, short wavelength, high power. And that tells you everything about the signal. But the real, I don't know, the interesting problem, or the thing that we spend all of our time really studying, is just noise. We're just studying, we're like, something like a zoologist goes around and studies animals of all different types. We are like zoologists of noise. And this is just the first, all this week I'm just going to be saying noise, noise, noise. And occasionally I'll insert some other word besides noise, but basically I'm just talking about noise. And shot noise is the first of these things. And we'll give a more sophisticated description tomorrow, but for the beginning you can imagine it to just be, as you usually do, that shot noise is, as its name implies, it's a Poisson process of counting the arrival time of photons. And you can, based on the amount of, the total number of photons that you have hitting the photodetector, you can look at the fluctuation. And the best you'll do is to have this fluctuating number of, square root of the number of photons hitting your detector. And so that will produce this kind of white noise that you can't get beyond. So if you're looking for signals and you're listening to the detector as if you're a audio detective or something, you're trying to listen for this chirping sound that Peter made, or something maybe more accurate, but close to that. Instead, you'll hear this hissing, and if I could, I would make this chirp sound on top of this, and then you could try to detect it. If you go on the web, you can find there's a website called Black Hole Hunter that lets you do exactly this trick, so you can listen to noise and signal at the same time and see how good your ear is for doing this signal processing. Uh, so many more developments happened, which we will get into throughout the week, but there are two chief ones, which led to the improvements in the later part of the 20th century. People turned the Michelson arms into FabryPerot cavities by putting a resonator here, or a mirror here. So this end mirror is maybe 100% reflecting, and this one is 99% or something reflecting. So each time the light approaches here, a little bit of the light can go in, and it goes around here many, many times. And each time the fresh light enters this thing, it builds up. And eventually, in the steady state, the power in here is much higher, maybe 100 times higher than the power that's entering by just the resonant effect. And then still, the field from these two arm cavities interferes destructively here and constructively in this direction. So you can take another mirror and put it here, and this recycles the laser power by bouncing it back in. So now the field which comes back and bounces from this one enters back in and constructively interferes with the light which is entering this place. And so it still seems like, well, then what do you do? Where does the power actually go? Well, it goes into just losses, because you resonantly build up the light and it bounces around in here so many times. The full power, so if you put 100 watts of laser power into here, 100 watts of laser power roughly is scattered away from these mirrors by the roughness and just goes into the walls of the vacuum chamber. So more or less, maybe 99 out of 100 watts does that. And the rest is absorbed in the glass. Yeah. So in this picture, this is sort of the rainbow of gravitational wave detectors. Indeed, there is a red side here for CMB detection. And I would say it might be, in the current time, the challenge is equally interesting or equally tough for all of these people. The inflation probe is the name of a mission concept or something, but a space-based detector of microwave background polarization could detect gravitational waves which have a scale of roughly the size of the visible universe. There's a gap here where we have no detectors. Pulsars, because the observation period is from sort of 1 year to 10 years, can detect waves which have frequencies of 1 to 10 years. In between here, it's missing here, but satellites within the solar system, like Cassini mission, they're not very strong limits, but they can detect signals that have sort of several microhertz frequency. That frequency band would be greatly helped by someone developing much better clocks, atomic clocks or laser sources on that time scale. Then there's this ELISA project, which is now the baseline date for launch has been moved a few times. I think the goal now is for the Europeans to launch it in 2034. And then there's this intermediate band, which I'll talk about on Friday. But all of the ground-based laser interferometers that we consider cover the band from something like 5 hertz up to 10 or 20 kilohertz. And so everything is acoustic. And yeah, and then the reason just for that is that any sort of detector on the Earth is limited directly by seismic vibrations, but then even more fundamentally, the suspended mirror that's there is perturbed by the fluctuations in the local gravitational field. So to give you an example, if a bumblebee flies around the chamber at several hertz, the gravitational field from this insect will show up in our signal. So the outside influence has to be really strongly shielded. And at lower frequencies, just the wind outside, pressure fluctuations in the air, density perturbations deep underground, they would limit the detector. So below something like 1 hertz, there's no hope for 1 hertz or 1 millihertz. There's no hope for terrestrial detectors. Yeah, so there is actually, it's not really, it's in some sense, you could call this a gravitational wave detector, in the sense that you have detected the presence of gravitation. You have detected the effect of gravitational waves, so it's a kind of detector. Around the time Yeah. I think within a few months of my birth, Russell Hulse had detected these anomalous pulse period from this pulsar he was looking for. He was in Puerto Rico using the Arecibo dish. He was a PhD student and kind of perturbed that he had found, he was trying to look for a pulsar and was sort of perturbed that this one wasn't acting like a real pulsar and giving a steady pulsing signal, but instead was time varying. And that sort of anomalous thing led to the discovery of this, what we call the Hulse-Taylor binary pulsar pair now. And it has, I don't know, I think it by itself has become one of the most stringent tests of general relativity. And basically because the precision on its timing is so strong and the fact that the observation period is so long. So discovered in 1974, in 1979 declared to be a real source of, that the fact that the orbit was decaying due to gravitational waves, and so it was the first observation of, it gave us the first hope that there would be a real measurable effect from gravitational waves. And then I guess this also says something. It's something like 15 years between discovery and Nobel Prize. So that means it would be 2030 before we get a Nobel Prize for LIGO. Oh, unknown. This is a slide I made 10 years ago or something. Every so often I update the plot because they put out a new data point. There's also more than this. The Hulse-Taylor binary was the first one, but now there's several more relativistic binary pairs, which are all doing very interesting tests. Some of them you can test the Shapiro time delay because the pulse goes quite close to the occluding neutron star and passes by. It's a great laboratory. Yeah, I have several copies of this timeline that I keep updating, but I'll tell you what all of these symbols mean here. So this is the early timeline. There's the Weber detectors, the Weiss concept, and then a lot of people started building these prototypes. The first working prototype was by Robert Forward, who was one of Weber's students, and he did it as a kind of part-time work that he could do while he was doing other work in Malibu. And this first one, he did some early signal detection just by using his ear to listen to the data. And he had two, and one person listened to one in this closet, and the other one would go into that room and put the interferometer there and listen to it. And they didn't see any coincident signals at around 10 kilohertz or so. But after that first phase, more serious prototypes were built. And this plot is just showing you the evolution of the strain noise spectral density versus time. And we're starting off here at these Weber kind of levels. By the end of it, the bars were competitive and really beating the interferometers for a long time. And then this inflection period here is when the large-scale detectors came on, LIGO, Virgo, Tama, and so on. And after that point, there was no more competition. Then these green dots, the blue ones here are all real, truly actual measured sensitivity. And these green ones are my personal extrapolation of what I think will happen in the next decades, based on what we know now. Of course, if there's some great, someone here maybe has some truly clever idea, we can have another inflection point, and it would be great. Yeah, Peter showed you a picture of the Louisiana detector. I'm just going to describe now in turn a few of the ground-based detectors, and you can see why they're different. The Louisiana one is in this wet, swampy region, and the other one in the US is in this dry, brown desert region. And there are I think, some interesting challenges which come from different location. Here there's poisonous snakes. Here there are also snakes. But here there's cows, and here there are no cows. And here there's a lot of storm and rain, and here there's no rain, but there's a peculiar thing of tumbleweed that occasionally covers the detector and has to be handled. It becomes a safety hazard. I showed you this thing about how the sensitivity changes with time, and it's true. It does change with time, and I say this because when the LIGO-India detector first comes on, you shouldn't expect it to come on with full quantum limit activity on the first day. It's I think if you go to the car dealership and you buy a car, you expect that as soon as you get onto the road, you can drive at full speed down the highway, and there shouldn't be any commissioning period to get the car working. But these detectors, in fact, take some time. We now expect, and I think it's reasonable to expect, these next generation of detectors will go much faster. But this was the time evolution of the first 4-kilometer detector, and you can see it took several years to get the first few decades in sensitivity. This dashed line at the bottom was the designed sensitivity based on the calculation of quantum noise, thermal noise, and these simple things. And you can see there's a lot more going on. These noise curves are a lot more detailed than this smooth trace. And this is why I say we're a zoologist of noises, because we had to, at each stage of this thing, we had to go through and understand all of these little bumps and traces and what are all these lines doing, and remove all of those. But after this period of time, it's hard to see this one. This one is 2006. So it's something like 5 years for this progression over several decades in sensitivity. And even at the end, there were some extra features here. But, well, the team was very dedicated. And so it eventually started working. Yeah, in making these lectures, I think we made some choice to leave out some material because it was too much detail and maybe not so interesting. But I just wanted to show this plot to you to show what are the sort of important factors, how many things have to be controlled, or what are the important factors in the system. This black trace, which you see here, is the actual measured output noise spectrum of the detector. And just to be more explicit, this x-axis is frequency, this y-axis has these funny units, meters per square root of hertz, or in some other cases I show a plot in units of strain per square root of hertz. What does that mean? It's displacement divided by 1 over inverse seconds or something like that. I think it's easiest to think about it in terms of some sort of astronomical detector or electronics detector. If you square this, then you get something like meters squared per hertz. And if you imagine out of your detector you have an electrical signal coming where the voltage is proportional to the displacement. So it's just linear transducer. And you can look at the energy in some frequency band. So you take the signal out and you make a 1 hertz wide filter at 100 hertz, and you look for how many voltage squared you get. And you just read out the energy you get from this filter. It's some level of power, and it's some volts squared, and you can turn it into meters squared. So the spectral density is telling you something like, if I had a 1 hertz wide filter at each point and I moved it around, what would be the displacement squared that I would measure in that band? And then you can add those up and make this kind of plot. So that's I think an intuitive way to think about it. Anyway, as you see, there's really dozens of noise sources here. And so in addition to the fundamental quantum and thermodynamic and seismic limits, there are a lot of technical problems here which come from the feedback systems and laser noises and vacuum systems, magnetic fluctuations of the ambient power, basically anything you can think of. The LIGO detectors are a very good microphone for all kinds of fields and noise sources. Let's talk about one of these other detectors. So the GEO detector is in Hanover, Germany, or just outside of Hanover, Germany. It's in this field you see here. Each of these arms is 600 meters. It is not an optical illusion. The arms are really not at 90 degrees. So it's, I don't know, maybe 80 degrees. It's a little less. So it still works. So it's not necessary for the arms to be a perfect L shape for it to work. Although it was smaller, the geodetector uh, is still very important because they have always been trying out some technologies which are a little more advanced than the LIGO detectors in order to both to increase their sensitivity and also to be used as a prototyping test bed. So they made these mirror suspensions to have freely falling test masses made out of all glass. They went beyond this technique of power recycling that I described to you, signal recycling, which I'll describe in a few days. And then they move the mirrors around by applying electrostatic force to them using this gold pattern. And they had a similar improvement in sensitivity over several years, got better and better. And at the end were, well, they're not ended, but as of this time, they had a strain sensitivity of around 10 to the minus 22 square root of hertz. But you see their minimum in their noise or their maximum in sensitivity was closer to 1 kilohertz than the LIGO sensitivity, which was lower frequency detector. In order to increase their sensitivity, rather than make cavities within the arms, they folded the beam one time, and so instead of getting just the 600 meters, they had effectively a 1,200 meter length by folding it one time. Yeah. The Virgo detector is the one which was probably closest in sensitivity to the LIGO detectors. It was is the problem I have all the time. It both, because it's gone through multiple phases, sometimes I will say was, and sometimes I'll say is, but it really means it's a continuous process. It's 3 kilometers long and located fortuitously, I think, in Pisa, so it's close to where Galileo did some of his early work. One of the main features which differentiates the Virgo detector from all of the other ones is that they decided early on in their work that they were going to place a huge effort into eliminating the influence of seismic noise from the detector. And whereas the LIGO detectors used to hold the mirrors with one loop of pendulum to give one stage of seismic isolation, and the geodetector had a few stages. The Virgo detector had really several. And this gap you see here is because they initially had room for another one here. So there would have been a 6 or 7 stage seismic isolator. And it's really very huge. This is the mirror, which is about the same size as the LIGO and Geo optics, and this is myself standing next to one of the prototype systems. So you can, well, you see how I'm not very tall, but still, this even goes off the page. But it's really a huge, huge structure. It's the dominating feature of the Virgo detectors. Other than that, the Virgo detector was quite similar to the LIGO detector, power cycled system with FabryPerot arms, roughly equivalent laser power use, and the sensitivity was nearly as good over the whole band. And this similar kind of plot that you've now seen a couple of times, and this is a little outdated. By the end of their work, they were really quite close to their also calculated design sensitivity, which was very close to the LIGO sensitivity. Now the Tama detector in Japan, and close to Tokyo, was the shortest of all three, and as a result, it was also in the end the least sensitive of all three. But in the early days, because they had an aggressive plan for how to make things work, they were the most sensitive detector in the world over this period, 2000 to 2002, even though it was only 300 meters long, and also due to the way that the system was set up there, the team was quite small. The team that worked on making the detector operate was only a few people, really, a few knowledgeable scientists at a time. So it was really, for those of us in the world who felt like we were in competition with Tama during those years, it was a little demoralizing to think, here we have our team of 100, and our detector is 10 times the size, and why are they still beating us? And they did very good. One of the things that they did is, Tama is really the inventor of this type of thing. I started creating this type of noise analysis for the detectors after seeing that they were already doing it. They, it seems a very natural thing now to say, what are all the possible limits to our sensitivity, and to plot them on one plot. But they were really the first ones to do that, and by doing that, provoke the rest of us to do it. Yeah, their sensitivity progressed quite a bit. They had this huge gap at low frequencies, which was a mystery for a long time. And they, at the end, just before the Tama was shut off, they also upgraded their system to make a huge vibration isolation system, and saw quite a lot of improvement. So what's happening next? I think Virgo and LIGO are pursuing similar upgrade paths, that there will be a dramatic upgrade of the laser power and optics quality and these kinds of things, and we're both aiming for similar sensitivity goals. And it's natural. The idea is to have a network where the data can be shared, and if the sensitivity of the detectors is very different, it doesn't make any sense. You can't do a useful you can't do a very useful analysis if you have 3 detectors of which one is 3 times worse than the other one. They all have to be sort of comparable for it to make sense. And Japan, the detector site where Tama is will not be used anymore for gravitational wave detection, although it still remains a lab. But the detector site will now be underground in this place called Kamioka, where the Super Kamiokanda neutrino detector is. And by going underground, really the main advantage is that the seismic surface waves will not be penetrating anymore, and so the initial environment that they have to deal with is maybe a factor of 10 to 100 better than the rest of the detectors. And I'll show you tomorrow or Wednesday. I'll show you the relative vibration levels of all of these different sites. Yeah, this view graph that I make can never be up to date, because the rate at which people are joining is too fast for me to keep up. But so I'm sure this is insulting to some people because I've left them off of this thing. It's at least 1 year old or 2 years old or something. But the LIGO collaboration, which makes all of this happen, is quite big and getting bigger. Most of these groups are not contributing directly to the building or the debugging of the detector itself. Most are involved in, or are doing some of that, but mainly doing the searches for astrophysical sources through the data. So it's not quite the model of high energy physics where everyone is contributing some piece of hardware. We say often, I think we show this plot of the future detector and the current detector, and this is meant to represent the space surveyed by the current detector, and this one by the future second generation detectors, advanced LIGO, advanced Virgo or something. This is true, but it's sort of a conservative statement that we're making. What it means is that in this around few hundred hertz region where we expect to make the main, we really expect to get the biggest share of signal to noise ratio for binary systems which have masses of 1 to 2 times the mass of the sun. Most of the signal comes from here, and so for those sources we expect to get a 10-fold improvement in the range, and because the detector is kind of uniform antenna pattern, a factor of 1,000 in the rate. So that's very powerful. It means that every time we make a square root of 2 improvement in the noise of the detector, we get very excited, because it's a square root of 2 in sensitivity, so a factor of 3, and or square root of 2 cubed in the rate. So potentially it could be huge, but it's even better at the very low frequencies. So if it turns out that most of the astrophysical sources in the out to the range of the Virgo cluster or within the local neighborhood or so are heavier, if they're black holes with solar mass of 10 to 100 or 1,000, then the sensitivity improvement we're getting is more like several orders of magnitude. And so these kinds of conservative estimates that I'm making about the rates can be once per month or something like that is really, it's only for these sources which we are really sure exist. I think now the evidence for things like intermediate mass black holes is much more strong, and so they do exist. We just don't. I think within a factor of 100 or 1,000, we don't know uh, the numbers of the population. So this is just a comparison now in some quantitative way of the difference between the early LIGO detector and the advanced LIGO. So you can see maybe the biggest differences here. The laser power within the arm cavities used to be 20 kilowatts, and we expect at the full levels for it to run up to 800 kilowatts. I don't know. How many people here have used lasers in the tabletop? How many people have not used lasers in the tabletop setting? Okay, good. Most everyone has. This is, I think 800 kilowatts is kind of a difficult number to imagine. What's it really mean? I wonder what's the highest power laser, if you're allowed to say, what's the highest power laser you used? Is there anyone used more than a 1 kilowatt laser? Oh. 10. All right, that's pretty good. Still smaller than 20. Yeah, so I mean, it's a little bit different from having a pure laser like this. We have this stored power within the FabryPerot cavity, but we don't really have access to it. But when once you get beyond this level of, it's around 5 to 10 kilowatts where the big change happens, that the thermal distortions become overwhelmingly strong, so that you can no longer operate without the adaptive optics. And the other thing that happens, which is very surprising, is that it's hard to believe because we have no experience with it in our daily lives, but the mechanical force which acts on the suspended mirror is completely dominated by the radiation pressure of the light once you get beyond something like 10 kilowatts. And at the level of several kilowatts, we noticed it as a kind of annoyance that, well, all of the eigenfrequencies of the suspended mirrors were changing by factors of 2 or something. What to do? It was destabilizing our control systems. But in between this time, when we've gone to 40 or 50 kilowatts, it changes from the picture that Peter showed you of sort of independent optics into one where the modes of the system are so dominated by radiation pressure that you imagine it as it's back to the bar detector almost. You have a L-shaped optomechanical rigid body that you are trying to control. And so it's a qualitatively different thing. And then I'll get into some more of these later in the week. But qualitatively, this is the biggest difference. Advanced Virgo is doing roughly the same thing. They are already starting out with a huge benefit in terms of the attenuation of seismic noise. I think in the end, their design doesn't call for as much sensitivity right in the minimum, so the shape will be slightly different, but the detectors ought to be very comparable, and by the time scale of 2018 to 2020, we should have the 3-detector LIGO Virgo network working, and then in the next few years, hopefully also India and Japan. GEO is doing some interesting things also with the technology development. They're the first detector to put in non-classical states of light. So I'll describe what it really means, but at first, when you hear about it, it seems as if it's some sort of cheat and we must not be calibrating our detector right, but the use of squeezed light injection into these interferometers allows us to make displacement measurements which are below the level that you would naively expect from the Heisenberg limit. We're not, in fact, beating the Heisenberg limit, but at first it appears to be so. And tomorrow I'll describe how that's done. But it's now working at GEO, and they've been operating with squeezed light for more than a year. It's no longer just a research-grade tabletop experiment, but it's something real that's happening. So finally, the Japanese detector, as I said, the new one will be underground. But in addition to being underground, it's also using the technique of cryogenics. So one of the limits that we'll describe this week will be the thermal noise in the detector that will really just causes vibrations of the front surface of the mirror and limits your displacement sensitivity. Kagra has done a lot of research into using cryogenic crystalline mirrors. So everyone else has been using silica, this amorphous substance. They've gone the route of using sapphire, which has a very high mechanical Q factor, very high density, low absorption. It's very, very smooth, and when you cool it to temperature of around 15 to 20 degrees, all of these optical and mechanical properties become much better as well. So it's going to be very challenging, but if these techniques work of going underground and becoming cryogenic, then it should be a technique that all of us can use. So this is just a cartoon of how it would work. They expect to use the similar kind of isolation system that the French-Italian Virgo collaboration will use, although modified somewhat to work for cryogenics. This is just, I guess, an expectation of how much improvement we get from them. So this is a picture showing the antenna pattern of the worldwide network, excluding India, just showing the US LIGO detectors and Virgo, and then how that gets modified with the addition of the Japanese detector. And we'll show you a similar plot for the addition of the Indian detector, but it's basically these gaps in the antenna pattern are filled in. So it means that as the Earth rotates, we would be blind to any sources in these directions, but it's filled up by the Kagra detector. Let me just skip this. And finally, for ground-based detection, again, it will be more detection or more detail about this, but basically this is the most ambitious detector for terrestrial detection that we have, and it's to make a triangular shaped. This is a concept that's been studied by the Europeans. It's to make a triangular shaped detector underground, which is 10 kilometers on each side of the triangle, and it's a multi-interferometer. So one piece of the triangle is meant to work for high frequencies and one for low frequencies, and so they are somewhat different designs. And this is to really, the idea was to think big. What's the ultimate we can do underground? And their expectation is that using the most advanced technology they can imagine, that there would be sort of an order of magnitude improvement over this upcoming generation of detector, and then also working down to a few hertz or so. And the interesting thing about getting down to this band is that you can now start to see, I think as you could tell from Peter's audio demonstration, that the low frequency part of the binary in spiral lasts for a very long time. And so when you get down to this level, the sources of that kind will last for an hour or so. And so instead of the detection of transients, we would be in the game of detecting almost continuous signals for much of this band. So it would be qualitatively yet another very different detector. I should say this is very optimistic, but to I don't know, to add some cold water to this description, I think in none of the cases did the detectors end up with the sensitivity that was estimated in these kinds of plots. Although in some cases we got very close in some frequency bands, and so it's a mixed bag message, I would say. In the cases where the real detector made it to the level of the predicted sensitivity, it was done by basically discovering new facts about the detector and making significant upgrades. And so this is not really, this is perhaps all possible, but it will be more difficult than we expect. But if it wasn't difficult, if the strain sensitivities weren't so tiny, why would we do it? It would already be done, I guess. So that's all I have. Yeah, medium. they get some factor just for making the detector longer. If you could, uh, I think something like 50 kilometers length would be optimum, because we would drop a lot of these fancy technologies. But there are a lot of problems to that. Of course, the cost is worse and so on. And so this at the very least, this will be a €1 billion project for one site. And then they still don't have the capability of doing coincidence detection and pointing and all those things. They expect to use, yeah, I can give you a link. There's a very thick booklet that they wrote on it, but it's a long list of technologies.
Increase the path time, you obviously increase the sensitivity in the lower frequency range, but do you pay any penalty in the higher frequency?
At first you would, but if you change the parameters of the optics, then you don't have to. Up to some frequency. So if you keep optics the same, but if you keep the reflectivity of the mirrors and the time constants the same, and you increase the length, then you will start to cut away your high frequency sensitivity. But you can readjust it so that you don't lose it.
50 kilometers is more than the wavelength.
Yeah, we can still do detection if it's more than the wavelength. I think the kind of quasi-static picture that we use for detection, where we assume that the gravitational wave is basically a DC effect, is no longer true. But you know, if you think of the case of these space-based detectors like the LISA or something, they're strongly into that limit already. So it's just the calibration of the detector becomes more difficult, and there are certainly some nodes at which you can't make any detection, but you know, detection can still be made.